Last class you learned to see recursion and 80-112, the tree of calls and the stack that runs them. Today, we put that site to work on a whole family of problems that shared one demand. Try every possibility. Know how many subsets does a set have? What are all the orderings of these items? How many ways can you fill this grid? These are not solved by a clever formula and 8202. They are solved by systematically exploring every option. And the disciplined technique for doing that is backtracking. The whole idea fits in 3 words and 8112: choose, explore, unchoose. You make a choice, you recurse to explore its consequences, and then you carefully undo that choice and try the next one. Do that at every step, and you walk the entire space of possibilities without ever losing your place or missing a case. Today, we will make backtracking concrete on the 2 most fundamental examples, and 82112. Generating all subsets of a set and all permutations of a list. Master these 2 and you have the template for dozens of harder problems. Let us begin. Here is our path for today. First, what backtracking actually is. Second, the choose, explore, unchoose rhythm at its core. Third, the decision tree that lets you see it. Fourth, generating all subsets. Fifth, generating all permutations. And sixth, pruning and 82112, how backtracking stays fast. Let us dive in. Let us start with what backtracking really is, because the name describes it perfectly. Backtracking builds a solution, one choice at a time. You add a piece, then another, going deeper toward a complete answer. But here is the crucial part. The moment a path cannot possibly work, an 82012, a dead end, a rule broken, or simply a branch fully explored, an 82012. You undo your last choice and try a different one. You back up and track a new path. That undoing is the whole trick, and it is why the technique is called backtracking. Think of walking a maze. You go forward down a corridor. If it dead ends, you do not give up on the whole maze, an 80C212. You walk back to the last junction and take a different turn. You only ever abandon as much as you must. Then explore the alternative. Backtracking is exactly that, applied to any problem where you build an answer through a series of choices. What makes it systematic, an 8112, and this matters, an 8112, is that by always trying every choice at each step and always undoing before moving on, you are guaranteed to explore every possibility without repeating any, and without missing any. It is exhaustive and it is orderly. That combination is what lets backtracking correctly solve problems that ask for all solutions, or for any solution that satisfies a set of constraints. So the takeaway, backtracking builds a solution one choice at a time, and the instant a path cannot work it, undoes the last choice and tries another, an 8212, a systematic, exhaustive way to explore every possibility, like walking a maze and backing up at every dead end. Every single backtracking solution you will ever write follows the same 3-beat rhythm. So let us name it clearly. Beat 1, choose. From the options available at this step, pick one and add it to your current partial solution. You are committing tentatively to this choice and seeing where it leads. Beat 2, explore. Recursion A202, call the function again to make the next choice on top of the one you just made. This is where you go deeper down the current path, building the solution further until you either complete it or hit a point where you can go no further. Beat 3, unchoose. This is the beat beginners forget, and forgetting it is the #1 backtracking bug. After exploring, you remove the choice you made, an 82-112. You restore the state to exactly what it was before, an 82-1, so that you can cleanly try the next option. If you do not unchoose, your leftover state contaminates the other branches and your answers come out wrong. Choose, explore, unchoose, make it, recurse on it, take it back. So the takeaway, every backtracking solution is the same 3 beats and 8212. Choose an option and add it, explore by recursing on what remains, then unchoose it to restore the state and try the next and 8212. And forgetting to unchoose is the single most common bug. Just as with plain recursion, Backtracking becomes obvious the moment you draw it, and the picture is a tree. Every choice you can make is a branch. So from the starting point, each available option leads to a new branch, and from each of those, the next set of choices branches again. The result is a tree of possibilities, and A2012, the decision tree, and A2012 that lays out every path your search can take. Read the tree carefully, and it tells you everything. Each node is a partial solution, and A212, the choices made so far on the way down to it. Each leaf at the bottom is a complete solution, and O200 fill, a full sequence of choices. The branches between them are the individual choices that lead from one partial state to the next. And now the key insight. Backtracking is nothing more than a depth-first walk over this tree. You go down one branch as far as you can, and A212, that is exploring. When you reach a leaf or a dead end, you climb back up one level, and A202, that is unchoosing, and A202, and go down the next unvisited branch. Choose is stepping down a branch, unchoose is stepping back up. The whole algorithm is just walking the decision tree, depth first, visiting every path. So the takeaway, every choice branches, so the search forms a decision tree, and A112, each node a partial solution, each leaf a complete one, and A112. And backtracking is simply a depth-first walk over that tree, stepping down to choose and back up to unchoose. Let us make this concrete with the first classic problem, generating all subsets of a set and A200, the power set. The choice here is beautifully simple. Go through the items one at a time, and for each item ask a single yes or no question. Do I include this item in my current subset, or do I leave it out? That is it. Two options at every element, and A2112, in or out. Now apply the rhythm. Choose an A220. Include this item. A2 200 Explore all the choices for the remaining items. Then unchoose it and A202. Take it back out and A200. Leave it out and A200. Branch instead. When you have made a decision for every item, the subset you have built is complete. Record it. Do this for all items, and every possible combination of yes and no gets generated exactly once. The decision tree here is a clean binary tree, 2 branches at every level, one for NA20, include NA20 A21, and one for NA20, exclude AK20 AK20, and 1 level per item. A set of 3 items gives a tree with 8 leaves and 85, 205, the 8 subsets from the empty set to the full set. That is why a set of n items always has 2 to the n subsets, n binary choices multiplied together. So the takeaway, to generate all subsets, the choice at each element is simply include it or leave it out, and H200 pate, a binary decision tree, 1 level per item, and H212, and exploring every yes or no combination produces the entire power set, all 2 to the n of them. The second classic is permutations and A2112, every possible ordering of a list of items. The choice is different, and seeing that difference sharpens your understanding. Here, at each step, the choice is, which item do I place next? And you may pick any item that you have not already used. So the first position can be any of the items once you fix it, the second position can be any of those that remain, and so on. Each step, you choose one of the still unused items. The rhythm is the same. Choose an unused item and place it next, mark it as used. Explore N8084, recurse to fill the remaining positions from the items still available. Then unchoose N824, remove it from your arrangement and mark it unused again, N824, so the next branch can place a different item in that position. When no items remain, you have a complete ordering. Record it. Notice how the tree differs from subsets. At the top, there are n branches, 1 per item. At the next level, n-1 branches, since 1 item is now used. Then n-2, and so on, down to 1. Multiply those, and you get n factorial leaves, n A2112, every ordering. 3 items give 6 permutations, 4 give 24. The tree narrows as it deepens because each choice removes an option. So the takeaway, to generate all permutations, at each step you pick any item not yet used, mark it used while you explore, then unchoose it and A2112. The tree branches n, then n-1, and so on, producing every ordering, all n factorial of them. Backtracking as described visits everything n A2112, but its real power on constrained problems comes from not visiting what cannot help. That is pruning. Pruning means, before you descend into a branch, check whether it could possibly lead to a valid answer. If it cannot and it is seek to wolf, a constraint is already violated. A partial solution is already invalid and it is seek to wolf. You skip that branch entirely. You do not choose it, you do not explore it, you cut it off. The payoff is enormous, and here is why. Each branch you cut removes not just one node, but the entire subtree beneath it, an A2112, potentially thousands or millions of paths you never have to walk. Cutting a branch high up in the tree saves you everything below it. This is the difference between an algorithm that finishes instantly and one that runs for hours on the same problem. Think of a puzzle, like placing queens on a chessboard, so none attack each other. The instant you place a queen, that attacks an existing one. That whole line of play is doomed and A2 out. So you prune immediately rather than filling in the rest of the board only to discover failure at the end. Good pruning is often what separates a backtracking solution that is merely correct from one that is actually usable. Explore only what could work. So the takeaway, pruning checks a branch before descending and abandons it the instant it cannot lead to a valid answer and 8-200 fall. And because cutting one branch skips its entire subtree, good pruning turns a hopelessly slow, exhaustive search into a fast, practical one. Because backtracking explores possibilities, it is important to be honest about its cost and 8224. It is powerful, but it is expensive. Look back at our 2 examples. Subsets make 2 choices per item, so the tree has 2 to the n leaves and A212 exponential in the number of items. Permutations make n choices, then n-1, and so on, giving n factorial leaves and A2112, which goes even faster than exponential. These are not small numbers. 20 items already give over 1 million subsets. 10 items give over 3 million permutations. What this tells you is when to reach for backtracking and when not to. It shines when the input is small, or when strong pruning cuts most of the tree away, or when you genuinely need every solution and there is no shortcut. It is the wrong tool when the input is large and a smarter method and A200 file. A formula, greedy choice, or dynamic programming and A200 file exists. Recognizing which situation you are in is a real skill. So the practical rule is, use backtracking when the search space is small enough to walk, or prunable enough to tame an A212 wolf, and always estimate the size of the tree first, using exactly the counting you learned last class. The decision tree does not just organize the search, it tells you, in advance, whether the search is even feasible. So the takeaway, backtracking is exponential and 85 wall 2 to the n subsets, n factorial permutations, and 85 wall, so it is powerful but best when the input is small or heavy pruning tames the tree. Always size the tree first to know whether the search is feasible. Let us close with the habits that make backtracking reliable, because the technique is easy to get subtly wrong. First and most important, always unchoose. After exploring the choice, restore the state to exactly what it was before you made it, and A200, remove the item you added, mark it unused, undo the change. A forgotten unchoose is the classic bug, and it produces answers that are wrong in maddening, hard to spot ways. Make choose and unchoose a matched pair every time. Second, get your base case right. Every backtracking function needs a clear condition for NA200. This solution is complete NA200. 200, all items decided, the board full, the target reached, NA200, at which point you record or return the solution and stop descending. Without a correct base case, you either miss solutions or recurse forever. And third, prune as early as you possibly can. The higher in the tree you cut a doomed branch, the more work you save. So check your constraints the moment you make a choice, not at the very bottom. And add a too hinty one: failing fast is the whole point. Unchoose faithfully, define completion clearly, prune aggressively. Those three make backtracking both correct and fast. So the takeaway? Write reliable backtracking by always unchoosing to restore state after exploring, defining a clear base case that captures a complete solution, and pruning dead branches as early as possible, and 80-12 all, the match choose and unchoose pair being the habit that prevents the most common bug. Let us gather the whole class in one breath. Backtracking builds a solution, one choice at a time, undoing a choice the moment it cannot work. Its rhythm is 3 beats and 8-12. Choose, explore, unchoose, and 8-12. In every solution you write, it is a depth-first walk of the decision tree. Each branch a choice and each leaf an answer. Subsets come from an include or exclude choice at each item and 82 hull, the whole power set. Permutations come from picking any unused item each step and 80-212. Every ordering. And pruning cuts dead branches early, taming a search that is exponential by nature. Next class and 8-12, backtracking 2, and queens and constraint puzzles where pruning truly shines, one idea at a time. That is backtracking and